Folks, if you're turning in a quiz for somebody who's not here today, you cannot turn in this quiz. That's cheating, and you get a 0 on this quiz, all right? In order to get credit for quiz 27, you have to be sitting in this room at 12:50 or 12:49, all right? So I'm going to be a little bit earlier than that, then you're not going to get credit for quiz 27. And as some of you know, you can't get quiz 27 wrong unless you write down the word elf in the wrong place, all right? Just a second. Or red shoes, or Christmas shoes, all right? In the wrong place.
I didn't hear anything you said.
Would you listen to me? Guys, take out a half sheet of paper. Oh, yeah, it's all worked out there. Lucy, does anybody not have a partner with whom they can get a half sheet of paper? You want to split one with Lucine here, or?
I have paper.
No. I don't want you turning in a whole sheet. I just said that.
I can cut it in half.
Huh?
I can cut it in half.
Yes, but I don't want you just cutting in half and him cutting it one in half. I want you cutting one sheet in half.
Are we saving paper?
Yes, that's what we're doing.
Okay. Why are you getting so feisty?
Because you guys aren't listening to me. I'm telling you exactly what to do. You're sitting there doing the other crap right here. Stop doing that. Listen to me. Do you understand? I don't want you wasting paper. I don't want a whole sheet of paper. I don't want you just cutting one in half for yourself, Lucine. Cut it for somebody else as well. You can't hear this?
You're not on.
You can't hear this. Rowan, can you hear what I'm saying? Bridget, can you hear what I'm saying?
Okay, you split one.
Like I'm standing right next to you? Anyhow, I will be showing you something about quiz 26. And as I was saying to those people who weren't actually paying attention, you are going to be expected to turn in the answers to that when you come in on Monday after Thanksgiving break. Understood? All the questions have been posted. I only got to 88, so that's fine, Larry. Some of the answers you're going to get today, all right, you can see some of those questions. I won't go back to them. We talk about this. What some of those questions ask about is words like dehydrogenase. And instead of like you did before in other crummy classes, just say, no, lactate dehydrogenase. Magic, blah, 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 lactate. What the heck can lactate dehydrogenase do? One of two things. Catalyze either this reaction or this reaction. And it's just like pyruvate dehydrogenase, which we might get the chance to talk about a little today. Yeah, it's the same thing as lactate dehydrogenase. Guys, it can't be. A dehydrogenase is going to catalyze a redox reaction, which I think you all know can easily go in either direction, right? But the name of that enzyme tells you which thing it would catalyze the oxidation of. Why would that be? Because a dehydrogenation is not a dehydration, it is a dehydrogenation. And what am I doing to something if I'm dehydrogenating it? What do you got, Mark? You get a better answer to that one.
Take a hydrogen.
That's what Melanie said too. And you guys didn't call taking away hydrogens taking away hydrogens. You called taking away hydrogens. Say it out loud. Starts with an O. You're oxidizing it. That's the same as reducing it. Are you serious? Lactate dehydrogenase does not both catalyze the oxidation and reduction of lactate. That can't happen. Well, it could happen. Yes, but not that enzyme can't be both. That's two different reactions. Understood? The oxidation of lactate is going to produce what? I'm not turning it again.
I didn't ask you.
I know, because you were looking at me like... The oxidation of lactate is going to produce pyruvate. What other reaction can lactate dehydrogenase catalyze? Okay. You can turn it in, guys.
I wrote something on the paper that said I'm here and my favorite Christmas movie is National
That's not a very good choice, is it? Anyway, okay, stop. She already did get permission to do what she just did right there before. What other reaction, besides the oxidation of lactate to pyruvate, can the enzyme lactate dehydrogenase catalyze? The reduction of pyruvate to lactate. What enzyme, what reaction does pyruvate dehydrogenase catalyze? Some of you are going to say, Rowan just said that. The reduction of pyruvate to lactate. No, it doesn't. Pyruvate dehydrogenase catalyzes the dehydrogenation of pyruvate, which is what? The oxidation of pyruvate. Yeah, it's a lactate. Guys, the oxidation of pyruvate does not produce lactate. Rowan just said that. No, he said the reduction of pyruvate produces lactate. And don't show me your hands, because all it's going to do is irritate me. I know some of you are saying, well, what's the difference? Guys, this is a thing that you should have learned back in high school chemistry classes. I didn't. You should learn it in freshman chemistry classes. I didn't. You should learn it in organic chemistry. You should have. I didn't. What are you so mad about? Because I don't want you to be like me. I want you to know this stuff like the back of your hands. Somebody says oxidation of this, I know it could possibly be produced. Oxidation of an alcohol. What do you get, Melanie? Ketone or aldehyde. Oxidation of a secondary alcohol produces a ketone. And oxidation of a ketone. That's not going to happen all that easily. Some of you will see in the Krebs cycle, it does happen on a ketone molecule. But I'm not oxidizing the ketone. I'm oxidizing something else that's attached to that molecule. And you're supposed to know what that is when we talk about that, just by the names of the molecules that we're talking about, okay? We'll get back to that in just a second. What I have to impress upon you right now is basically three things regarding glycolysis, all right? And the first one is that gluconeogenesis, which is not glycolysis, is not simply the reversal of what happens in glycolysis. Why would that be? The second thing I have to tell you about is how the glycolysis process is controlled. Why didn't you talk about gluconeogenesis first? Guys, because without talking about gluconeogenesis, the control of glycolysis doesn't make any sense. You can talk about it. We can just memorize these molecules. That's not helping you. The control points on glycolysis are what they are because of the problems that I have in gluconeogenesis. Finally, what I have to also find out about, or tell you about today, is how glycogen is involved in this process, all right? And I'm going to go through these things relatively quickly. I'm going to implore, beseech, entreat, beg you to look at, first of all, the slides and the questions on quiz 26, and on back tests, and say, I have to understand all of these things all at the same time. In gluconeogenesis, we are going to make molecules of glucose from non-carbohydrate molecules. As I was telling you at the end of class, and you should be writing this on your cheat sheet, the process in gluconeogenesis involves pyruvate being, first of all, made into oxaloacetate, which Mary told me has 4 carbons, which means it can't be part of glycolysis, all right? And why am I doing that? I'm going to make this oxaloacetate molecule into phosphoenolpyruvate, which means what has to happen to your oxaloacetate molecule? 2 things. If I'm going to make it into PEP, what 2 things have to happen to oxaloacetate? Maya, are you answering yourself? Or are you just kind of staring off into space? I can't tell for sure.
It has to lose a carbon.
It has to lose a carbon is an excellent answer. And that's the gain of what? Phosphate. Oh yeah, that's right. Where does that phosphate come from? Both the attachment of a phosphate, which requires energy, and the removal of the carbon dioxide, and the attachment of a phosphate requires a phosphate, and both of those phosphates are coming from triphosphate molecules. Folks, pay close attention to this. I'm saying triphosphates on purpose, because one of these 2 guys, and I always forget which one it is, actually uses a GTP. That counts as an ATP, which means that from here back to here in gluconeogenesis cost me not 1, but 2 high-energy phosphates. And we're going to just say they're both ATPs, as this textbook did right here, knowing that one of them is actually a GTP, the A and the G. And the U that I talk about later on are not important, all right? They're all treated as triphosphate molecules, and to make those things is going to cost me ATP. That's why we can say it's basically the same as an ATP. Understood? I'll explain more about this, especially when we get to the Krebs cycle, where it's a bit more important, okay? From here to here. That has to happen twice. Now, on your cheat sheet, you will notice that this reaction, all right, is drawn with the arrow only going in that forward direction. Is that absolutely true? As I was yelling before class, and it was yelling because Leandra said she heard me in the women's room, which is 4 doors down and closed by another door and across the hall. Because it's really, really important. Guys, the process of glycolysis. I'm seeing a couple arrows going in one direction. Is it true that they only go in that direction? No, they don't. So why are you drawing them that way? Because for all intents and purposes, inside your cells, they only go in one direction. Now first, let's back up a step. How would you know that they go in both directions? Because guys, every reaction in biochemical situations can go in both directions. Why would you consider a reaction irreversible? Because the conditions are such, not the enzyme's problem, the conditions are such that I can't get the reverse reaction to take place. And what specifically is it about a reaction that makes it irreversible? The concentration of products relative to reactants is considerably lower than the equilibrium concentrations. If they are at the equilibrium concentrations, is the reaction going in the reverse direction? Yes, as fast as they're going in the forward direction. And if I increase that ratio a little bit, then the reverse reaction happens a little bit more. If I increase the concentration of reactants and lower the concentration of products, or both those things simultaneously, then it goes a bit more in the forward direction. But when you've got reactions like phosphoenolpyruvate reacting with ADP to form pyruvate and ATP, having a delta G0 in the ballpark of a negative 7 kilocalories per mole, and in your cells, that actual delta G is around a negative 5 kilocalories per mole, that means the ratio of products to reactants is way below the equilibrium concentration. All right? And as such, you can do all you want with the enzyme, but it says I can only do what this reaction is allowing me to do. I can't do magic. I know some of you are just finding that out right now, but you're supposed to learn about that in your other biology classes, but certainly in this one, when we talked about enzymes. Do enzymes change delta Gs? Have you ever seen a picture in other classes where it shows you the enzyme, the catalyst, does not change the delta G? Everybody's seen that picture in numerous other classes. Here you're saying, yeah, we actually talked about how some of these guys do their job, and none of it has to do with changing the delta G, which doesn't change the equilibrium constant either, correct? That is a constant value. It does change the ratio of products to reactants, but it can't make a reaction that has too high an equilibrium concentration be at equilibrium, right? It wants to get there, but if the reactants are constantly being removed or products are constantly being supplied, then it's always going to be kind of going in the forward direction. In the case of gluconeogenesis, if this reaction essentially is irreversible, then to get around it, I have to come up with some other reactions. Not just changing the delta Gs of the enzymes, because they can't do that. These are the two reactions that circumvent this. Reversible, 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 reversible. Right? This reaction in glycolysis, look at your cheat sheets, is the arrow going in both directions. Why is that? Because again, like this reaction, and like this reaction, the concentration of products is not high enough to allow the reaction to reach equilibrium. All right? In the first case, it's way favoring the formation of products. The reverse reaction basically never happens, but it does. It doesn't happen exactly the same way in the reverse direction, nor does this one. Now listen to me carefully. In gluconeogenesis, this molecule becomes that. That's the reverse of what happens in glycolysis. No, it's not. In glycolysis, this molecule and this molecule become this and this. In gluconeogenesis, this becomes that. What is the difference between those two statements? I like the look on your face, Melanie. You just said it's the reverse. No, it's not. The reverse of the glycolysis reaction would produce what else besides fructose 6-phosphate? ATP is the correct answer. If I just take a fructose 1,6-bisphosphate molecule and take the phosphate off, that's an easy reaction. That kind of wants to happen. And you put it back on a, do you see it putting back on an ATP? No, I just go from here to here. That would mean, folks, and this does happen inside you, it also happens, as I understand it, in hibernating animals, that if I went from here to here, and then went back this way through the activity of this enzyme, which is just a phosphatase, just takes the phosphate group off, all I would be doing is wasting ATPs. Why would hibernating animals be doing this? Corinne, did you ever play rugby when it's cold outside? And you're fine, but as soon as you stop running around on a rugby field, that's when you're doing fructose 6-phosphate, fructose 1,6-bisphosphate, right back again. Why are you doing that? To waste ATPs? No, to generate the heat that goes along with the losing of that phosphate group. Oh, and that's also why when I get done shivering, I'm so damn tired, because I'm just wasting all these ATPs just for the heat purposes, all right? During that rugby match, during the tennis, during the track, whenever you're doing that soccer, basketball, whenever you're doing this, you don't do that. You go in this direction in muscle cells, and you go in this direction in liver cells. So you're taking that energy requirement for making this back into glucose molecules, that you don't get ATPs back here. It's going to cost me still 2 ATPs going this way, and cost me an ATP going this way per pyruvate molecule. I don't get them back in this situation, and the liver says, I'm fine with that. I can take more fat molecules. I get a better choice of oxygen than you muscle cells do. Your brain is always saying, I need this stuff. I need the glucose molecules, and I need the oxygen. And as most of you recognize, when you overdo it athletically, if you're not trained to do those kind of things, you stand up even too fast. My brain says, whoa, what's going on right here? Because it says, you can't do that, all right? If it goes on too long, your brain says, I'm shutting down right now, and you pass out. So it still gets a chance to get all the glucose molecules and oxygen that it needs, and if you don't get it to it, then yeah, you could have a problem, all right? The glucose molecules being made into pyruvate, we're going to get 2 net ATPs made this way. If I took that pyruvate molecule and made it back into glucose, according to these processes in gluconeogenesis, circumventing this reaction, which is kind of irreversible in glycolysis, and this reaction, which is kind of irreversible in glycolysis, and this reaction, which is kind of irreversible in glycolysis, with different processes, and simply the removal of a phosphate group. From here to here, I get 2. From here back to 2 of these guys cost me 6. I don't get any back in the situation. Thus, gluconeogenesis and glycolysis occurring in the same cell is just going to waste 4 ATPs. If the muscle cells are saying, we'll do the glycolysis, then what does the muscle cell do with those pyruvate molecules under anaerobic conditions, and why? When you are out sprinting, playing basketball, playing rugby, even playing tennis when you're sprinting out there, all right? What will those pyruvate molecules that the muscles really can't use do with the pyruvate molecules? Reduce them with what? With NADH. Where did that NADH come from? The other reactions of glycolysis, where the NADH, the reaction of glycolysis when NADH was produced. This reaction right here, producing what? A poison, an end product, a waste product, a byproduct. I don't want this thing, I want the NAD+. So it gets rid of the lactate molecules, and the liver says, hey, I got enough oxygen, I'll make some of those lactates back into pyruvate. That's the only thing you can do with it. Either that or just completely excrete it, all right? You can't do anything else with lactate other than making it back into pyruvate, and the liver's going to do that. Muscle cells can't do that. They want the NAD+. Liver cells have some NADH. They'll use that, NAD+. They'll make the lactate molecule back into pyruvate, and then go through all these processes right here. The combination of glucose being used in muscle cells and the lactate from those muscle cells being converted back into glucose molecules, for what purpose? For liver and for muscle and brain cells to use those glucose molecules, is a little cycle. Glycolysis in the muscles, gluconeogenesis in the liver. The cycle is called the Cori cycle. And what it costs you is basically 4 ATPs, which is not a good deal. Because as some of you know, we can get a lot more energy, a lot more ATPs out of the complete oxidation of a glucose molecule, but I don't always have the time nor the oxygen for all those reactions that take place. And this little loss of ATP will go on for a while. As some of you may have heard in your biology classes, the fight or flight mechanism, it'll go on for a long time until you completely collapse. If whatever it is that's chasing you is scary enough. And you'll just keep right on running until I run out of stuff. We don't usually have that kind of terror anymore, fortunately, all right? You don't get chased by wolves, you don't get chased by tigers, you don't get chased by other bad people in most cases in this country, and most other countries too for that matter when it comes right down to it. So we invent things like soccer and basketball to kind of spend energy that way, and that's where we're going to do this, all right? We can only go on so long because overall it is a net loss of ATPs. The reason that this and this are a control point, as asked on either quiz 25 or 26, is that although they are irreversible, if I'm controlling this enzyme right here, I'm gonna reduce the amount of energy that I'm gonna waste by going in the reverse direction. Which is why I told you, talking about the control of glycolysis, I can tell you what the points are. This is a control point of glycolysis, and this is a control point of glycolysis. And now you should be able to say, oh, that makes perfect sense. Because if I'm controlling this enzyme, that means slowing it down when I don't want the process of glycolysis to take place, then I'm going to reduce the amount of energy that I waste doing what? Going in the reverse direction. Imagine it this way. I'm a cell that doesn't control glycolysis. What happens is I just make a bunch of pyruvate molecules. When I realize, wait a minute, I don't want a pyruvate molecule right now. I don't need any energy for anything. What am I going to do with those pyruvate molecules? The smart cells will say, let's make them back into glucose molecules, but that's going to cost me ATP. If I go from glucose to pyruvate, and then realize, oh, I wanted to make those glucose molecules right into glycogen, which we'll talk about in a second. I should have just done that. But I didn't, because I don't control my glycolysis process, and suddenly I got to go through gluconeogenesis using 6 ATPs to make that glucose molecule. If I had stopped at PEP, how many net ATPs would I lose going back to a glucose molecule? Now, as Jess will tell you, looking at her cheat sheet, if you go from glucose to phosphoryl pyruvate and stop there because this enzyme is being told, don't do your job, all right? We don't need the pyruvate molecules right now. We don't need ATP. And then I go back from glucose to phosphoryl pyruvates. How many net ATPs do I get or lose? I see you doing some work in your head, Corinne, or are you talking about your shopping list for Thanksgiving?
No, I'm thinking about it.
Cranberries?
You're gonna like get one less out of.
I don't get one less. From glucose to pyruvate. How many net ATPs do I get? As Jess can tell you right now, because she's looking at her cheat sheet, I start here, I go down to pyruvate, I lose 2, I get 2 back. The net is 0, correct? If I go with that pyruvate molecules that I got back to glucose, I would lose 2 here, but that'd be it, all right? So from glucose to pyruvate in the back cost me 4. From glucose to phosphoryl pyruvate. Why would I stop there? Because this enzyme is getting the signals, don't do it. Don't do my job right here. So if this builds up, which forces these guys all back this way, only cost me 2 ATPs. And guess what? If this enzyme is also being told, hey, wait, we don't need these reactions to take place right now. I go from glucose to fructose 6-phosphate and stop there. To go back only cost me 1 ATP. The advantage of these 2 points as control points are that when I don't go into reverse reactions, once I've already made them, I waste less ATP, all right? That is a big point. They are mostly irreversible, not because the enzymes can't do their job, but because the conditions are such that the reversible reaction is not all that easy to do. So other processes have evolved, all right? Do all organisms do this? No, yeast cells don't do this. They make ethanol molecules, they don't do gluconeogenesis. Why would they bother? They don't grow if you don't give them sugar molecules. You can give them starches. They don't know how to use those things, all right? Which is why, those of you who make your own beer, Eric, you said something or other? Or you made wine or something like that, right?
No, my dad made beer.
Your dad made beer. Do you remember what he did? He took the barley, and then he heated it up for a while. What he was doing was trying to get the starches that were present right there into monosaccharides, disaccharides, because yeast cells know how to deal with those. You give them glycogen, they don't know what to do with that, all right? You give them cellulose, they have no idea what to do with that, all right? You give them sugar molecules from grapes. You give them sugar molecules from potatoes. Again, breaking down the starches that are present right there. And they'll say, yeah, we'll metabolize those molecules, choke them off. Like our cells get choked off, they make an alcohol. But instead of making the lactate molecule, which is the alcohol we make, why do we make that one? So we can get it back to glucose molecules, because we have cells that say, we know how to deal with that kind of crap. These cells say, forget it. We're just going to make ethanol molecules. We get a little bit of energy back from that, and we get the NAD plus back that we need to keep glycolysis going. And as I understand this, your yeast cells kind of like doing things that way. Even when they have oxygen, they will still sometimes make alcohols, make ethanol in most cases, for the yeast cells that I know. And some of you have experienced this, even if you are not into beer making. You keep your breads with have yeast cells in them kind of packed up. You can kind of smell the alcohol coming off in a little tiny bit. Mostly what they're doing is also producing carbon dioxide as they make that 3-carbon molecule pyruvate into ethanol. The other carbon, you guys all know ethanol has 2 carbons, right? The other carbon is the acid carbon that comes off as carbon dioxide, and that causes your bread to do what? To rise, right? And you say, oh, that's what's happening, right? That's what's happening. You're making some carbon dioxide molecules. Some of these yeast cells and any bacteria might completely oxidize the pyruvate molecule, also producing carbon dioxide. That's not really what you want them to do. You want them to kind of get some carbon dioxide produced in this process, and brewers definitely want the ethanol to be produced, which is why they definitely have to make sure that the whole process is choked off. Otherwise, they will completely oxidize those ethanol molecules or pyruvate molecules, or if not them, then some other organism will, all right, will burn it up there. And most of them are not supposed to have that in your beers and stuff. Anyway, okay? The process of glycolysis gets me 2 net ATPs, starting with glucose. What does it get if I start someplace else? As already recognized, start there. From glucose 1-phosphate, or glucose 6-phosphate, or fructose 6-phosphate, or fructose 1,6-bisphosphate. Some of you say, no, it's still 2 net ATPs. It's like, why would you say that? Because that's what I memorized in another class, and I yelled at you about this the other day. If you're not starting at glucose, it's not going to be 2 net ATPs. It's going to be something different, or it could be something different. So I have to memorize some new numbers? No, I'm just going to look at my cheat sheet. Well, I can't use that on December 6th. You don't have to count ATPs on December 6th. You have to count the ATPs on December 9th. And if you're smart about this, what it seems like Yasmin was doing, because she was writing down some structures of glucose molecules last week and isomers and things like that, she's going to start at glucose 6-phosphate. And then go down and see that I spend 1 going to fructose 1,6-bisphosphate, but I still get 4 back. So from here or here down to here, how many net ATPs do I get? You said this the other day. Colin, what you got? Or I thought you said for the day. From fructose 6-phosphate, glucose 6-phosphate, any high glucose molecule or thing in Michelle. It would be 3 net ATPs. And if you started at fructose 1,6-bisphosphate, Anthony, how many ATPs would you get? When you go to pyruvate?
3.
No, not 3. Fructose 1,6-bisphosphate. The net would be 4. Oh, because I'm not spending the 1 right here. Now that's kind of the stupid point. This and this are not stupid points. Why? Pay attention, folks. You are not responsible for knowing all this mathematics, all right? I did put these values in here. The reactions that we consider irreversible are irreversible because the conditions that you normally find inside cells are really, really, really hard to reverse. Very large delta Gs, -8, -5. All the other reactions, besides hexokinase, phosphatidylkinase, and pyruvate kinase, all right, have delta G values that are pretty close to 0, which means the reactions are pretty close to equilibrium, thus going either forward or reverse. Just a slight increase or decrease of reactants or products causes it to go one way or the other. The other 3 reactions, hexokinase, phosphatidylkinase, and pyruvate kinase, they are really, really tough to reverse. Thus, in glycolysis, they go forward relatively easily. In gluconeogenesis, actually, some of the reaction that goes away from what the actual reaction would be in glycolysis, okay? And I give you some numbers on this. Again, this is just showing you this. If the delta G of a reaction, like hexokinase, is a -5 under cellular conditions, to get to the reverse reaction concentrations, I would have to see this concentration change by about a factor of 1,000 or 10,000. If it doesn't happen, then the reverse reaction can't take place. Too many reactants, not enough products. Do not worry about the mathematics of this, all right? Maybe look at the delta Gs and see, oh yeah, here's ones that can drive the formation of ATP, here's ones that can't. We'll talk a little bit more about that, right? Again, I don't want you to memorize all the various allosteric effectors of the pyruvate kinase, hexokinase reactions. I am 100% certain that you may talk about this in more advanced biochemistry classes. What I want you to recognize is the molecules are going to shut down a process like this. First of all, don't shut it down. What do they actually do? They basically cause an increase in the Km of this enzyme right here to where the concentrations you'd normally be encountering of phosphoryl pyruvate ADP just won't allow the forward reaction to take place very well because the enzyme doesn't get activated the right way. Likewise, when you see some other molecules that promote this activity, all right, what they are doing is making the Km lower so that lower concentrations of these will be converted to pyruvate more easily. The enzymes aren't stopped. They're either made less effective or more effective. How do you overcome an enzyme that is less effective? You dump more reactants on it to make that Km be reached, You remember what KM is, right? This is gonna show up on the ACS chemistry final, guaranteed, they're gonna talk about this. It is the substrate concentration in which half of the enzymes are activated. It's a larger number that takes more reactants to make the reaction take place, according to the enzyme doing its job, which can easily be overcome simply by dumping simple sugars into your system. Eating soda, drinking candy, or eating candy, drinking beer, all those things that have lots of glucose associated with them, or that can be converted to glucose pretty easily, are going to be things that cause this reaction and the phosphatokinase reaction to take place much more easily. The other thing I want you to recognize, why would something like this shut this enzyme down? Why would something like this increase the activity of this enzyme? The ATP part is easy. ATP, if I got lots of that, I don't need glycolysis taking place because that's one of the purposes that I do glycolysis. If I already have enough ATP, what should I do with those glucose molecules? Store them away. Next slides, all right? If I have enough alanine, how is this related to this process? Who remembers what alanine is? Who, without the aid of the screen, can spell alanine? I sometimes get aniline as the spelling, and it's an entirely different molecule. What is alanine? Ross, we already did that part of this course. You're going to need it in about 2 weeks or 3 weeks, folks, for the final. What is alanine? It's an amino acid. And why would it be involved in this process right here?
Because its structure is really similar to pyruvate.
It is? How is it different from pyruvates?
Just that the amino.
It's an alpha amino group as opposed to an alpha ketopropanoic acid. And you guys all recall from nucleic acid metabolism how I can easily make the amino group into a keto group or vice versa. Folks, this is one of the sources of those amino groups that you're using to make what? What do I need amino groups to make besides amino acids? Rhymes with nitrogenous bases. I need the nitrogenous bases, and as you may recall, I showed you this. When you're putting a nitrogen on hypoxanthine to make adenine, you're replacing a keto group with a nitrogen. The keto group ends up being transferred to whatever amino acid is donating that group. In most cases, it's going to be glutamine or asparagine or aspartate, but those guys can also be converted to other molecules that we will talk about a tiny bit today, but certainly when we come back from Thanksgiving, all right? When I take that amino group off of this molecule and put it on someplace else and replace it with a keto group, it becomes pyruvate. Folks, this is the way that your amino acids get funneled into this overall process. You don't have a process like glycolysis or fatty acid oxidation that says, oh yes, here's how we use amino acids for energy purposes. They get converted to something that's part of glycolysis or the Krebs cycle or fatty acid oxidation, and in the process, they lose their nitrogens. When you are out sprinting, Maddie, you're going to use some muscle, and some of that muscle is going to be converted into glucose molecules simply by taking the amino acids from the proteins that are present right there, getting rid of the nitrogens to the urea cycle or making bases of some sort, and then making those molecules into pyruvate or oxaloacetate or alpha-ketoglutarate or succinyl coenzyme A or whatever, and you're not memorizing any of those guys in this class, but you are recognizing